Okay, I think we're ready to go on to our final perspectives presentation. This one is on the inner magnetosphere and ionosphere coupling, and the partners on it are Pontus Brandt from JHU APL and Mark Moldwin from UCLA. And I think they're doing a tag team.
Yes, right? We are. So we're taking a different approach to this. So this is the last talk before lunch. I think you're all tired. So we're trying to stay very basic here, and so opposed to previous speakers, we don't have 11 topics, but we have 3. So I'll make it easier for you. The task at hand here is inner magnetosphere and ionosphere coupling. We're not touching outflows at all, really much. And our purpose here is not to solve anything, but excite, entice, and provoke, just like previous speakers. And the way this is going about is that we're going to have alternating slides, pretty much. But before we continue, I think we have a...
Well, we were also asked to be provocative and controversial, and so we'll start it out. One of the reasons why we wanted to do a tag team, because we feel one of the problems of making any advance in IM or MI coupling is because of CEDAR and GEM. If we weren't distinct groups, we would have solved this problem. We would have realized we need observations both in the ionosphere and in the magnetosphere simultaneously. But because we're separate organizations and we have our own hats to wear, when it comes down to making priorities for funding and missions, usually MI falls to the wayside. So instead of having dueling IM 20-minute presentations, we're going to actually have a partnership to show how the GEM-CEDAR joint or CEDAR-GEM joint meeting should happen more often than every 6 years.
Sort of like a married couple.
Yeah.
So, so before we go on, let's have a little commercial break.
And then we also are trying to find new ways to get funding, so there's a couple commercial breaks throughout the talk. The first one, I'm the editor-in-chief of Reviews of Geophysics, and this time of a decadal survey, and we just lost a plug. Okay. Is a time for us to think back on what we've learned over the last 10 years. So I urge the community who has been spending time thinking about that to contact me on ideas for review papers in Reviews of Geophysics. There's a new paper that just came out on Friday by Kelly and all looking at equatorial electrodynamics. So I urge you to take a look at the Reviews of Geophysics website if you are looking at equatorial ionospheric physics. Okay, so now we'll dive in.
All right, so let's dive into this. This is sort of the approach Mark and I took. As Mark said, we're one or 2 different communities, and we attend the same meetings, and we also attend different meetings. So I guess what we're thinking of here is that we always think in terms of different physics. Do we think about conductivity, or do we think in terms of resistivity out there? Do we think in terms of collisions down there, or collisionless? And also, is the ionosphere, is that a 3D complex system, or do we tend to think that, well, the ionosphere is just a metal sphere, I'll worry about that later? I could, admit being that person at some point in the time. So MI coupling is where we meet in peace and harmony.
And so, of course, when you think about MI coupling, and we heard about the IMI panel and the SWIMI panel, and we know about CEDAR, GEM, and SHINE, and we have our own views of how that individual system works. But even when we describe what we do, we talk about that coupling. So when you talk about GEM, we talk about the magnetosphere. That's a solar wind-driven system, and that a lot of the dynamics within the magnetosphere is understood by understanding that coupling with the solar wind. But of course, the magnetosphere also dumps into the ionosphere, but when an ionospheric physicist talks about what are important dynamics for them, they're thinking of both what's coming from above and below, as well as internal instabilities. So you have to start thinking about neutral winds and dynamos, gravity waves, tides. We heard from Jeff Forbes about the importance of understanding what's going on at the turbopause and how those waves can make their energy dumped into the mean flow in the thermosphere. So MI versus IM is obviously a complete artifice or not the right way to think about it. We should think of it as IM or MI coupling as essentially looking at the same system. We have energy, mass, and momentum flowing in both directions, and to be able to understand any individual system, we have to have a complete systems approach. And so I think that falls in with the new CEDAR strategic plan, as well as where we're going in this next decadal survey.
All right, so the next couple of slides here, we're sort of trying to address why should I care? Are there any macroscopic effects that we see out there? My favorite example as a magnetospheric physicist is the entire configuration of the magnetosphere, or at least the inner magnetosphere. To your left here, basically you have the potential electric field in the magnetosphere without any coupling to the ionosphere. The little inset down here is an ENA image modeled, of course, of the ring current. You have the midnight sector here, noon, dawn, and dusk, and it happily sits in the pre-midnight sector. Now, if you start actually looking at what currents are flowing, as depicted here in this nice illustration, this is an equatorial projection of your plasma pressure. And as Mike pointed out before, this is the ring current plasma pressure, and it contains the dominating energy density in the magnetosphere. And it does drive currents just from force balance consideration. The blue lines here is the current system. And you can see once you get off the equator, you start dipping into the ionosphere with field line currents. And this is how I depict what the region 2 field line current really is. That's what you're looking at here. And of course, this is not a metal sphere. It's a highly complicated system of conductance and conductance gradients, and it is changing constantly in time. So if you do close this system through the complex 3D system of the ionosphere, you get an electric potential pattern like this. And it's not simple. And what happens in the magnetosphere? Well, for instance, the ring current shifts more than 90 degrees. It shifts its ring current peak or its pressure peak towards the post-midnight sector. So there is a very macroscopic effect we see directly at work.
And so obviously one of the problems our field faces, even if you're in the GEM or the CEDAR community, is the need for global observations at high temporal and spatial resolution. And in the magnetosphere, we can contemplate, well, how many single point measurements do we need to be able to measure everything, and at what cadence? And then we can go down to the ionosphere. If we need to measure things at 20-kilometer type of resolution, that's tens of thousands of ground-based instruments. I mean, it's just, we have this huge system, either in the upper ionosphere or in the magnetosphere. But when you look at the typical cartoon of magnetospheric physics, the question is, where is the ionosphere? Right? We don't have it labeled. With almost always this thin black line. But of course, from the CEDAR community, that we've been spending the entire career looking at that 3D coupled complex system. And just want to show again Joe Grabowski's beautiful view graphs, and I think Joe would appreciate it. One of the things is there's a set of these slides, and you always see just the fourth one. But I want to walk through what these actually telling you. This is a view of the sun with extreme ultraviolet on planet Earth if there was no magnetic field. And so what would we study? We'd essentially study the winds, the neutral winds, the collision processes driving the ion flows. We'd have gravity waves, solar-driven tides, and we'd have those dynamics. If you add a magnetic field, the next slide, you start adding a lot more complexity to it. And you start making this connection to the topside ionosphere and the plasmasphere. You start having ion outflow to fill the plasmasphere along those magnetic field lines. Equatorial electrodynamics start becoming very important as you start now having E cross B drifts moving the plasma vertically. And so you have this fountain effect. And then with pressure gradients and gravity pulling down that plasma, you start having structure and latitude with the anomaly. As you now have inflow from the magnetosphere and solar wind system, you start getting currents and convective flow at the polar region that drive neutral winds due to Joule heating that, as we saw, can propagate through the mid-latitudes and even cross the equator. And you have all different types of the electrodynamics. And so the idea of trying to study the inner magnetosphere or the ionosphere as individual components is ludicrous when you try to think of what actually determines the structure and dynamics. It's this coupling of both the equatorial and the polar region ionosphere together. And then storms even make it worse because you start blending the high latitudes with the low latitudes, and the mid latitudes become very complicated. And so we were going to concentrate on a few topics, and they're essentially, you could almost think of them as equivalent. We have SAP, SEDS, and plumes, and we're thinking of them as what causes them, what are they, and where are they. This is from a paper from using DMSP data, Wang and Foster, and this is a typical polar cap DMSP flight. You're looking at number density, the magnetic field, electrons, ions, and the flow. And you can recognize the auroral ovals and the polar cap, and bring your attention to this subauroral feature. You have this large sunward flow. This is the signature of the flow due to a SAP's electric field in the subauroral region. It's in the dusk sector, and it's observed fairly often, but particularly under enhanced geomagnetic activity. And so from the ionosphere, we draw these perspectives of region 1 and region 2 currents flowing in and out of the ionosphere. The trough is a convectively driven region of low density, low conductivity. And as you attempt to close those currents through that low conductivity gap, you have an enhanced electric field that drives that sunward or westward flow on this dusk side. And so you can start thinking of these SAPs as this truly the MI coupling signature of the subauroral region. But of course, the currents that are flowing are from the auroral regions and the ring current.
So let me, I mean, this is one of the topics where we sort of agree already, but I wanted to point out another picture that I've come across from just a purely magnetospheric perspective. And think of your electron plasma sheet boundary just by the virtue of how the electrons drift and how the ions drift. You can then start arguing, well, I mean, ions are usually positive and electrons are usually negative. And so you would get in the dusk sector or pre-midnight sector, you get an outward electric field, and this could be the SAPs, right? So what's wrong with this picture? I'd say everything is wrong with this picture. First of all, there are no currents. Second of all, I don't really believe in charge separation. I guess that's a religion. So that's what's wrong with this picture. And as Mark pointed out, this is pretty much what is going on in some sense. And with this slide, I want to point out two sides of the same coin, just to stir in your mind a little bit. The first scenario, pretty much what Mark pointed out here, is that you have your field line currents being driven by your pressure gradients in the ring current, which is the orange blob here sitting outside the plasma sphere. And these currents, they close through the magnetosphere, as I explained before. And of course, when they close through that low conductance gap, they generate, in quotation marks, an electric field. And that electric field, within quotation marks, pushes plasma. And that gives rise to your flow velocity. That's your E cross B down here. And then, of course, since the trough has a very low conductance, if you looked at the conductance gradients, it's fairly easy to convince yourselves that the E field maximizes in that conductance trough. And of course, then your flow velocity will maximize in that trough. So that's one simple picture that people are modeling successfully. However, there's sort of another Gedanken experiment out there. Picture this. There's already convective flows in the magnetosphere. Essentially, the solar-wind interaction is stirring the two-cell convection pattern in the ionosphere. If you have a patch of very low conductance, blue skies and clouds, the convecting field lines, they will just zip right through that low conductance region. So that's another way of sort of thinking about your enhanced SAPS flow velocities. Open questions, I don't remember. Should I or, okay. After each topic here, we want to sort of summarize with open questions that are still out there. I want to point out this, one of my favorite studies by Paul Quinn. If she happens to be here, she should take honor. And there she looked at simultaneous electric field measurements and density measurements in the magnetosphere as well as in the ionosphere for a very beautiful, stable event, textbook event of a SAPS and the narrow SAID event. But basically, the open questions can be summarized as follows. First of all, the general question is, how true is it that the E field is similar in the IT system and in the magnetosphere, and how do they evolve together? When does it break down? Why does it break down? And also, how does the ring current pressure gradients and the currents and the ionospheric trough, how do they evolve together? This is probably perhaps the least known areas. What really creates the narrow SAID channels and what makes the trough deepen? And where is the trough in the magnetosphere? Sometimes we see it, sometimes we don't.
So the question is, so what? Why do we care about SAPs? What can they do? And if you have a large electric field, you're going to move plasma. And what is that result of that movement of plasma? Again, John Foster's seminal work with some early image EUV observations, taking a look at the storm-enhanced density observations that had been observed for decades on the ground with incoherent scatter radar, TEC, and other observations. Essentially, here's the famous North American plasmasphere with the storm-enhanced peeling out. And if you look at the velocity of this set event, you can see that the plasma flow is flowing out toward the day side and the cusp. When you looked at the image EUV picture of the plume that was pointed out early in some very simple convective experiments by Joe Grabowski, the formation of this plume, these ionospheric signature and this intermagnetospheric structure overlap. So we now have a connection between the plasmasphere, the intermagnetosphere, and the electrodynamics in the mid-latitude regions. And so one of the things you would wonder is when we look at the total electron content or F-region enhanced densities, how does that actually map out into the intermagnetosphere? Is there a role for ion outflow or even downflow in regions? And what is the fate of that plasma as it gets convected to the day side? And so when you look at, this is a tomographic reconstruction of the topside ionosphere using GPS TEC from 200 to 1,000 kilometers. And you can see this trough feature, this difference between the main plasmasphere and the auroral precipitation. And this white dotted line is a field-aligned map from image EUV at simultaneous in time and space. And you can see that there's a very good correlation between this equatorward edge of the trough and the plasmasphere. And when you zoom in and change the contrast of the density contours on this tomographic reconstruction, you can see that there's this high-density plume extends above and out into the topside ionosphere. And if you look at the next slide, RPI and image EUV, not quite simultaneous observations. This is from Garcia and al. A few years ago, where they looked at image RPI data. This is the plasma wave instrument, where you're looking at essentially the upper hybrid frequency trace here. And that maps with the plasma number density. And you can see there's two high-density regions labeled A, and this plume or trough feature out here labeled V. And image, as it flew through perigee, first flew through this high-density region at high latitude and then into the plasmasphere, indicating that even at high latitude and high altitude, you can see observations of this dense plasmaspheric plume. But again, the question is, what is that field-aligned density distribution? And so some of the open questions on SEDS again, what is this field line? Can we actually have remote sensing from plasma instrumentation that we have been doing for decades and decades, from whistlers and space-based observations, to probe those closed intermagnetospheric flux tubes, the connection between the dynamics of the SED plume plasma and the magnetosphere with the mass budget? What role do these plumes and these storm-enhanced density play in the dynamics? And what we haven't talked about, because the previous speakers, but when you talk about ion outflow and O+, we know that there's a significant outflow of cold O+, and it's observed as a cold ion torus, heavy ion torus in the intermagnetosphere. What role does that play in storm dynamics and coupling?
All right, so let's go into the third topic here, which is commonly known as prompt penetration electric fields. So the upper plot here shows you a schematic of the whole idea. I think many of you know that they do detect vertical drift as Hickamarka, and they track the interplanetary electric field very well with about a 10-minute lag. And of course, studies like Mike Kelly's study show that it's usually a ballpark of a 15% efficiency of that penetration. So why does it penetrate? Well, I mean, first, when I thought about it a long time ago, I went, well, that's easy. I mean, you have a changing magnetosphere convection pattern that sort of reaches those altitudes. And you look at it some closer and you go, wait a minute, it takes about easily up to 30 minutes to change that magnetospheric convection pattern. So there is something else very fishy going on.
Yeah, so just impromptu controversy, the damn Rice convection model of shielding, when you're thinking about how do you get electric fields to mid-latitudes and equatorial regions, when you have that Rice convection model idea of that is shielded out instantly, you can't get those electric fields down, so it has to be neutral winds. But of course, we know it's a combination of the neutral winds and these penetrating electric fields. But the observations show that the equatorial ionosphere, the electrodynamics, responds nearly simultaneously with convection changes and input. And so that led Kikuchi and al. To essentially develop a ionosphere ground waveguide, and suggested that it's an electromagnetic speed of light type of propagation from the auroral region to the equatorial ionosphere. Peter Chi, using Tamao's old MHD model, looked at, could you explain it with these alphanic velocities instead of E and M velocities, and showed that the signature that you see on the ground as a function of latitude can be very well explained by MHD waves propagating along different trajectories, either as fast mode waves across the field lines, coupling to field line waves that reach the ground. And so there's still an open debate on how does these prompt penetration electric fields get from changes in the solar wind into the magnetosphere, from the high latitude regions to the low latitude regions. And one of the things to think about when you, as the closed field region, the equatorial and the mid-latitude region, even though they're maybe 45 degrees and below, that's definitely the most part of the world where people live in, the largest part of the area of the sphere. But when you start thinking about this plus or minus 20 or 30 degrees latitude, you have to think about these field lines essentially extend into the topside ionosphere. So it's not going to be coupling into the magnetosphere. So the direct route of energy, mass, and momentum has to be circuitous. And so that's a big area of research right now, is understanding these electrodynamics in the equatorial region.
Okay, so the open questions on penetration are pretty simple. We already said it. How does it get down there that quickly? I mean, we're talking very quickly. And also a very important question still out there is you have all these effects from the dynamo-driven E-fields, neutral winds, and from Joule heating at higher latitudes. How do you separate that from the prompt penetration electric fields? And of course also, how does the ring current modulate all of this? Let me go on and show sort of a provocative slide from Janet Kosira, of course. And I happen to like this one, so let me go through it. It talks about UT effects. And this is obviously Lanol plots here. This is date, 22nd January, 23rd, 24th, and 25th. And this is another satellite. And take a look at these little wiggles here. And when Janet first saw this, she didn't really believe it, but it sure is tempting to say that these wiggles look very, very similar on different days, and they occur at the same UT. Same is true for the GO satellites. It's very provocative. Could it have something to do with dipole tilt? David Sybeck is shaking his head, as usual. But our objective is to be provocative, and I think we're succeeding. So let me go to another pitch for planetary magnetospheres. We do see, just like Mike said, we do see UT effects or rotational effects in other magnetospheres. This happens to be Saturn, which is very mysterious because Saturn's rotational axis is almost perfectly aligned with its dipole axis. And what is shown here is, this is pretty much the night side over here, and these are, of course, ENA images of global remote ENA images of the proton population in Saturn's magnetosphere. This is the post-midnight sector, and about 10 hours and 40 minutes apart, we see these injections in the post-midnight sector. And that is still a very, very outstanding mystery.
Yeah, so as part of this UT effect, obviously one of the things that is different in the magnetosphere-ionosphere system is the day-night terminator, and then we also have an offset dipole field. So our conditions in the ionosphere driving a lot of these UT signatures. And so one of the things we're always taught is that we have symmetric hemispheric conjugacy, and we also have spherically azimutally symmetric. And so I think that's another area of active research for this next decade, is to understand the role of the ionospheric conductivity and the offset of the Earth dipole in driving a lot of the periodicities we see in geomagnetic activity. And obviously, we've heard the magnetosphere and ionosphere described as a RLC circuit, and what we actually need from each other is, give me the conductivities and give me the voltages and whatnot. And that's true. It's in the sense of the magnetosphere, when we looking at developing global models, everything depends on the conductivity model you use for your ionosphere. And there's no real good conductivity models. You usually have to have fudge factors to add to it. And then understanding the distribution spatially of conductivity. We have often aurora ovals, but nothing else imposed on it. From the ionospheric perspective, of course, we need to know this energy input, these field line currents, and how the ring current distorts the inner magnetosphere, driving those currents. And as we heard from the long laundry list of things we need at 20-kilometer resolution at high cadence, essentially, we need to know what's going on in the solar wind from above for both the magnetosphere and the ionosphere, but as Jeff showed, we also need to know about the energy input from below, the gravity waves and the tides, and how that they can put periodicity into the upper atmosphere, thermosphere, ionosphere that can drive dynamics.
All right, so obviously when we give a talk like this, we usually end with the future. There's a buzzword, system level view. But I'm coming to realize that the GEM and CEDAR community is actually the community that is actually working on it. There are other communities out there, and they're not really working on it. So I think I preach to the choir that we need to really take a system level view. And what that practically means is, of course, studies and observations that follow global dynamics in both systems simultaneously. And we see a lot of those studies. hand in hand with that goes global modeling and data assimilation. I think it's fair to say that the system is so sophisticated and complicated that we cannot sketch it on a piece of paper and look at data and plots and understand it. We need global models to understand it, it's clear. And also, we can't even achieve nowcasting, I think, without data assimilation. So that's another venue that is right around the corner, or actually people are working on it successfully. And as I said, again, comparative planetary ionospheric and magnetospheric science, the lessons there, they go both ways. Both communities, both the planetary and we can learn from it. There are a lot of people in the planetary community that doesn't know much about the terrestrial magnetosphere and the ionosphere. Bob Strangeway had a good example of the atmospheric escape from Earth. We have of course estimated the atmospheric escape, but the Mars and Venus people, they estimated the atmospheric escape, and it wasn't until they compared the two numbers that they noticed that something was obviously very wrong. The magnetic field does not shield the atmosphere. It might be the other way around, in fact. So there's a big mystery there. The problem, I think, is that, of course, the interest is probably there, but funding is not. But again, I think GEM is the right forum, and I think last year we had planetary tutorials, and I think that's a very good start. So with all that, I think we will conclude. Mark, any concluding remarks?
Thanks.
Thank you.